In the last class, we have introduced RSA public key encryption scheme. This RSA actually, this R is for Revest, S for Shami, and A for Adelman. They together invented this, they designed this crypto system. So let us once again recap. So in RSA crypto system, it is actually based on the difficulty of factoring large integers. So we choose two large primes P and Q and set the modulus n to be product of these two large primes. Generally, these primes are each of these primes P and Q are of 1024 bit. 1024-bit primes. Now the plain text space and ciphertext space are Zn. Actually, the plain text space, every plain text will be raised to the power b modulo n, and means your plain text will be raised to the power the public key of the recipient. B is the public key of the recipient raised to the power public key modulo n, and the decryption is the ciphertext to the power the secret key modulo n. This is the concept. Now, for the correctness, we need this y to the power a. This decrypt means this should give you back x. If y is generated by raising x to the power b, then this will give me back x. So y to the power a raised to the power y to the power a essentially means x to the power b raised to the power a. If y, this is your y, so y to the power a means x to the power b raised to the power a. Modulo n, we are working modulo n. Now, since this a is the secret key and b is the public key, and they are related by this congruence. A and b, their product is congruent to 1 modulo phi n. We choose b from 1 to phi n and then find the modular inverse of b, that is a inverse. This was the idea. So two large primes are generated and set the modulus n to be pq, and phi n is p minus 1 q minus 1. Then randomly selects b in from this range, and so that b and phi n are co-prime in order to have the modular inverse of b modulo phi n. So find the next step is finding the modular inverse of b. We call it A. So A is B inverse modulo phi n. That means we are getting the congruence relation AB is congruent to 1 modulo phi n. Okay, so this B is public, this N is public, and secret is A. Okay, so when you encrypt, you use the public key of the recipient, and for decryption, the decryptor, that means the recipient is having the matching secret key A corresponding to B. He can simply raise the ciphertext to the power A. Now for the correctness, we need this to be equal to 1. Why it will be 1? Because we have the equation, we have the congruence relation AB congruent to 1 modulo phi n. AB congruent to 1 modulo phi n. So x to the power AB, you can write this AB is 1 modulo phi n means AB equal to 1 plus some constant into phi n. Okay, so AB can be written as 1 plus k, some k times phi n. So if you substitute this, you are getting x to the power 1 plus some k into phi n. Now you can write it as x into x to the power phi n raised to the power k. Now x to the power phi n, that is 1 by Euler's theorem. Okay, provided x and x belongs to Zn star. So here your plain text space, this x must be co-prime to n. Otherwise the correctness will not hold. Okay, so your plain text, every plain text will be an element of Zn star. So this x must be co-prime to n. And in that case, by Euler's theorem, x to the power phi n will be 1. Okay, so if you use that here, then you can get this equation. This will give you back x this is your correctness. And okay, now let us go through some more solutions, I mean some more problems, how to solve some more problems. So this is modular order of invertible modular integers. So already we have we know what we mean by order of an element A relative to n. Order of, so we choose A, an integer A from 1 to n less than n. A is co-prime to n, A and n are relatively prime. Then the order of A modulo n, we denote it by this. Order of A modulo n is defined to be the least positive integer k, such that a to the power k is giving you 1 modulo n. Okay. Now by Euler's theorem, we know that a to the power phi n is always congruent to 1 modulo n. So order of A modulo n always get less or equal to phi n. Okay, this we have already stated, and this actually comes from the definition of order and Euler's theorem. And not only that, it can be proved this order of A modulo n is actually a factor of phi n. It divides, this order of A modulo n divides phi n. Okay, and another point to note, that order of an element A relative to n, this is defined only when A and n are co-prime or relatively prime. So order of A modulo n is defined only for A and n, if whenever A and n are co-prime. Okay, so how to find the order? So exhaustively you can find the order. Suppose order of orders modulo n when n is 7. So so I will calculate the powers of 7 modulo n. So compute the orders modulo n of all positive integers less than n and relatively co-prime to n. It's only for those elements which are less than n and co-prime to n, their order will exist, modulo 7. Okay, so all the elements we list down here, all the elements which are less than 7 and co-prime to 7. Okay, so there are total 6 elements. And the powers, a to the power k, I am calculating this value, a to the power k, and check which is the least value of k for which it is you are giving 1. So we keep on powering. So for this element k equal to 1 to all are 1. So least k for which it is giving me 1, this is this. So the a equal to 1, it has order 1. So for a equal to 2, keep on powering 2 to the power 1, 2 to the power 2, 2 to the power 3. So when you take 2 to the power 3, we are working modulo 7, so it becomes 1. Then once it becomes 1, then it repeats. Then again 2, 4, 1 like that. So here, first time I am getting 1 here. So the order of 2 modulo 7 is 3. Similarly, a equal to 3, keep on powering it, and the first time you are getting here. And essentially this k equal to 6, phi n, phi n means phi 7, this is 6 here. So in this column, the last column, it is always 1. For every element, it is always 1. And for 3, I can see that it is essentially a primitive element in Z7 star, because its order is essentially equal to phi n, that means 6. Okay. Similarly, A4 you can calculate. This is the order. Order of 4 is 3. First time you are getting 1 here. Okay. Order of 5 also. Order of 5 is phi n. So 5 is also a generator of Z7 star. 3 is generator. 5 is also generator or primitive root modulo 7. And A equal to 6. Order is 2. Okay. And we know that how many generators Z7 star will have? Phi of phi 7. That means 6. That means 2. And these are the 2 generators. So you can, this way you can find the generators. you can find the generators. Keep on powering. Essentially, we don't have to power. We don't have to take all the powers. We can see that later. So for modulo powers of 8 powers of modulo 8 of integers relatively prime to n equal to 8. So the elements which are relatively prime to 8 are these 1, 3, 5 and 7. So you can see that the powers of these integers for a equal to 1 this is 1, a equal to 3 this is 2, 5 also 2, 7 also 2. So there exists no element in this Z8 star that attain the power equal to 5. 5 it is 4. So so it is the power becoming a to the power k power becoming 1 before reaching here. So there is no element which is a generator of this. Essentially, this is not a cyclic group. You can argue from the structure of this also. It is not of the form required form. This modulus n is not of the form 2, 4 or p to the power k or 2 times p to the power k. P is odd prime, k is positive integer. It is not a cyclic group. This way also you can check. There exists no element in Z8 star that has order phi n. That is 4. Powers of modulo 21. Here also, just check this. This also does not have it does not have a generator because it is not in the required form. So it is not a cyclic group. Z21 star is not a cyclic group. Okay, so this integers which are relatively prime to 21. We can list all these integers which are relatively prime to 21, and then keep on powering up to 5 1 up to 5n. 5n means 521, that means 12 up to 12. Okay, last column, that means k equal to 12. This column all will be 1, and the orders you can find this way. So this way you can check that Z21 star is not cyclic because there exists no element in Z26 to 21 star with order 521. Means before reaching this power, it is giving you 1 before that. So the order is for a equal to 2 order is this one, k equal to 6. For a equal to 4 order is 3, like that. Okay. So, so here we have made all the powers. Means we have taken all the powers from 1 to 5 in. So we don't have to do that. We can further speed up our calculation. How? Suppose a and n are relatively prime positive integers, and suppose k is a positive integer such that a to the power k is 1 modulo n. Then order of a modulo n must divide k. Order of a modulo n is a divisor, is a factor of k. Is a factor of k. Okay, and in particular order of a modulo n is a factor of phi n. And also if I and j are non-negative integers such that a to the power I is congruent to a to the power j modulo n, means if ij are non-negative integers, then a to the power I is congruent to a to the power j modulo n. This holds if and only if I and j are congruent modulo order of a modulo n. Okay, so if we are working modulo n, then in the powers we can work modulo order of a modulo n. And since order of a modulo n also defines phi n, we can work these powers modulo phi n also. So when working modulo n, exponents can be reduced modulo order of a modulo n. Okay, we have mentioned all these results earlier. Now we are going to give a proof of these facts. So this relation that order of A modulo n is a divisor of phi n, that means we don't have to calculate. So we know order of A order of A must divide, or A modulo n must divide phi 21. That means the order of any element in Z21 star must be a factor of 12. So we will try only the factors of k for those case. We will find the power for which that k which is a power of which is a factor of 12. So factors of 12. So 5 I don't have to consider 5. I don't have to consider 7. Okay, like that. Okay, so all the powers you need not to calculate, only the factors. So the factors are essentially 2, 4, 6, 12. Okay, 2, 4, 6 and 12. So and 1 also. 1 is essentially that element. So 2, 4, 2 also 3. 2, 3, 4, 6 and 12. 12, this column you don't have to calculate by Euler's theorem. This is 1, and the other you have to check whether it is giving you 1. If in that way you can decide whether a primitive element exists or not, and what is the primitive element. So this way we can find the primitive element of Zn star. So this actually simplifies your calculation. So you don't have to find all the powers of A. Only the factors, you have to look into the factors of phi n and check whether A to the power those factors giving you 1 or not. Okay, so the proof is very simple. So if this is the relation, this congruence, if you have this congruence, A to the power k is congruent to 1 modulo phi n, then means if order of A, we have to show order of A modulo n divides k. If order of A modulo n does not divide k, then I can apply division algorithm. So when I divide k by order of A modulo n, there must be some remainder. So R is suppose remainder. So I can write divide k by order of A modulo n, quotient is q, R is the remainder. So this remainder lies between arise within this range. So it is 0 less or equal to R and less than order of A modulo n, by which we are dividing k. Okay, the q and R, these are integers. So I have this relation, A to the power k is congruent to 1 modulo n. So this here I put k value of k, you get A to the power order of A modulo k, order of A raised to the power q, A to the power R is congruent to 1 modulo n. Now by the definition of order, this value is 1. A to the power order is 1 modulo n. So this value is 1. We are getting A to the power R is congruent to 1 modulo n, where R is less than the order of A modulo n. So this is possible only when R equal to 0. Because by the definition of order, order is the least positive integer such that A to the power order is 1 modulo n. But we are getting another integer R which is less than order of A, so and A to the power that power R is 1 modulo n. So it, since R is less than order of A modulo n, this relation holds only when R is 0. So k must be q times order of A modulo n. There will be no remainder when you divide k by order of A modulo n. Okay, so otherwise I will get a contradiction. Okay? Contradiction to the definition of the order. Order is the least positive integer for which A to the power this order is 1. But here we are getting R integer R which is less than the order and for which this relation holds. This is contradiction unless R is 0. Okay. So order is a divisor of k in case we have this congruence. And second result is just straightforward. By Euler's theorem we know if A and n are co-prime, then A to the power phi n is 1 modulo n. and by applying the previous result, this phi n must divide order of A modulo n. Okay, you take this phi n to be k. I am getting a relation by Euler a to the power phi n is congruent to 1 modulo n. So by this result, order of A modulo n must divide phi n. This result. And the next result also, you just go through the next result. This is also very straightforward. Okay. Now when you are working modulo n, then in the exponent you can work modulo the order of A modulo n. This proof is also written here. You just go through this, or you can do it by yourselves. Now the next order of power formula. Order of power formula, it says that if A, J and N are integers greater than 1, positive integers, and A is relatively prime to N, then order of A to the power J will be equal to order of A divided by GCD of J comma order of A. Okay, order of A to the power J, this gives you the order of power formula. So if you know the power order of A, then you can find order of A to the power J, order of the power of A. So order of power of A is order of A divided by GCD of that power comma order. So you can say that when this GCD denominator, this GCD is 1, then order of A to the power J is same as order of A. Now already we have seen that how many generators it has, how many generators, how many primitive roots Zn star has. Suppose Zn star Zn star is cyclic, and how many generators it will have. So if you know one generator A, then other generators are given by A to the power J such that J and J and phi n are congruent, phi n are 1. J and phi n are co-prime. Their GCD is 1. So already we have mentioned this result. So this actually comes from this general formula. Okay, so it means so how many generators it has? If Zn star is cyclic, then it has a primitive root. Suppose A is a primitive root. That means order of A is phi n. Order of A is phi n. And if A is a generator, then what are the other generators? Other generators are A to the power J such that J and phi n is 1. So so number of generators is phi of phi n. So that is what it is noted here. If A is a primitive root modulo n, that means this value A is a primitive root modulo n means order of A modulo n is phi n. And this equal to 1 means A to the power J is also a primitive root modulo n. If A is a primitive root modulo n and this is 1, then A to the power J is equal to order of A, equal to phi n. So A is a primitive root means A to the power J is also a primitive root. Under what condition? Under the condition the denominator is 1. Okay, so A is a primitive root modulo n, and this denominator, this GCD is 1. This means A to the power J is also a primitive root modulo n. This is the corollary. If G is a primitive root modulo n, then other primitive roots modulo n are the same as the modular power of G to the power J modulo n, and this J runs through all the positive integers less than and relatively co-prime to order of G modulo n. If G is a primitive root modulo n, that means order of G is phi n. Then other primitive roots modulo n are the same as G to the power J modulo n, where J is co-prime to J is running through all the positive integers less than phi n and co-prime to phi n. So that's why number of generators or primitive roots modulo n is higher phi n. So proof of the theorem, you can, proof of the theorem is written here. It is not, it's just a sketch is given here. Okay, so you just go through this and it's not written properly, okay, and also some mistakes are there. You do it by yourselves, okay? You do it by yourselves. Okay, the next, so this type of questions I will ask in your tests, okay? So if possible, do each of the following: compute order 7 modulo 59, find integers between 1 to 59 whose modulo 59 order is 22. Find primitive root modulo 59, primitive root of 59. Find the exponent j such that g to the power j is 7 modulo 59. Okay, so in this case you are asked given g, where g is a primitive root that was found in part C. So you find a primitive root. So this g is given, this primitive root is given. You have to find which power g to the power j is giving you 7 modulo 59. That means you have to find the discrete log of 7 with base g and modulo 59. Okay, modulo 59. So how to do that? Okay, so first one is compute order of 7 modulo 59. Now we know order of 7 modulo 59 divides phi of 59. Order of a modulo n divides phi n. Okay, so phi n, you calculate phi n. So first job will be to find the order. You have the modulus, you have to find the phi of modulus. Phi of modulus here it is prime. So the value is 59 minus 1. So now you factor it. So there are how many factors? 2, 29 and the product 59 itself. So you have to check whether what is the order of 7. Okay, so order of 7 modulo 59 will be either 2 or 29 or the total of 559, that is 58. It should be or 29 or it should be 58. Okay, 58. So its order is either 2 or 29 or 559, that means 58. So just check whether 7 square is giving you 1, 7 to the power 29 is giving you 1, and 7 to the power 58 is always 1 by Euler's theorem. You don't have to check that. So 7 square and you want modulo 59. Okay, so keep that in mind. So 7 square is 49. So it is not 1. 7 to the power 29. So you can go for fast exponentiation method. So binary representation of 29. So this way it is done. 29 is this, 2 to the power 0, 2 to the power 1, 2 cube, 2 to the power 4. So essentially 7 to the power 29 will be 7 to the power 16, 7 to the power 3, 7 to the power 8, 7 to the power 4 and 7 to the power 1. Okay. So calculate this value and you reduce modulo 59. Okay. So this is 7 and 7 to the power 4. If you reduce it, keep on multiply and reduce. 749, 3 7 you multiply, then reduce, and with the reduced value multiply the fourth one. That way it will get 41. 7 to the power 4 is 41. Okay. Similarly, 7 to the power, if you reduce it, you calculate, this is giving you 1. So order of 7 modulo 59 is 29. 29. Now the third question is, so it is 7 is not a primitive element. So if it is also not 1, then its order must be 58. Okay, but here the order is here it is 1 means the order is 29. Next question is find an integer between 1 to 59 whose modulo 59 order is 22. So order of an element should be 22. So in order that an element in between this has order equal to 22, 22 must be factor of 59. 22 is not a factor of 59. So there does not exist any element from 1 to 59 whose modulo 59 order is 22. So this question answer is no. No integer exists. So no such integer exists. For modulo 59 order is 22. Third question is find a primitive root of 59. So finding a primitive root modulo of prime. So what I will do, I will start from so the primitive elements, the elements of Z59 star I have to consider. So I will start from 59 is prime. So how many primitive elements will have? Phi of 559, that means 28 primitive elements. So how to find a primitive root modulo 59? So you try by simple brute force approach. Okay, we will adopt this brute force approach. We start from a equal to 2 and find its order. So possible orders are factors of 559. That means 2, 29 or 58. So 2 to the power 58 will always be 1. So I will check whether 2 square is whether 2 square not equal to 1, 2 to the power 29 not equal to 1, and 2 to the power 58 will be 1. So in that case 2 will be primitive element. So I have to check whether these lower powers are not equal to 1. If it does not hold, then I will instead of a equal to, so a means if 2 to the power 2 square is not 1, fine. 2 square is 4, it is not 1. 2 to the power 29 calculate, 2 to the power 29 it is calculated, it is also not 1. Okay, so 2 to the power 58 is 1. You don't have to check that one because by Euler's theorem it is certain that 2 to the power 58 is 1. So 2 is a primitive element. Okay, so fortunately in this case 2 is our first attempt with this brute force search is successful. So a equal to 2 is a primitive element. But in certain cases when it is suppose 2 to the power something to the power 29 is 1. Then it is not a primitive element, so we will check for the next integer which is co-prime to next least integer which is co-prime to 59. Okay, and check whether same experiment we will apply on 3. Okay, so 3 to the power 2 I will check, 3 to the power 29. So in this case I don't have to go beyond 2 because we are successful in our first attempt. Okay, sometimes you have to go for 3 then 5 like that. Okay. As I said earlier, that finding primitive root modulo prime, this is there is no good algorithm. Generally, this the brute force approach we adopt, and within 2-3 attempts, we generally get the primitive element. Now, the last question was the discrete log question. So primitive root, I find the primitive root here, g equal to 2 is a primitive root. So I have to find for one value of j, 2 to the power j giving me 7 modulo 59. Okay. So to find this j, we will go for so we will apply this order of power formula. So so this j I will vary from 1 to phi of 59. Okay, so let us work it out. J equal to 2. So so we have to find j such that is this relation hold. So 2 to the order of 2 to the power j modulo 59 is order of 2 to the 2 modulo 59 divided by GCD of j order of 2 modulo 59. Now order of 2 modulo 59, I know this is 58. Order of 2, this is 2 is a primitive element, so this is 5, 59. That means 58, 2 into 59. And this is GCD of j comma 2 into 29, is 59, 58. Okay. So this is 58 divided by this one is so GCD from here I can write GCD of this equal to order of this divided by 2 into GCD of this equal to 2 into 29 divided by order of 2 to the power j modulo 59. That means 58 divided by 2 to the power j is 7. So order of 7 modulo 59. Already I have found order of j 7 modulo 59 in the first question, first part of this question. So 58 by 29. So the value is 2. So GCD, this GCD of this equal to 2. This means what? Means I will narrow down my search of j. So GCD of j comma 2 into 29 equal to 2. That means j must be even. Okay, so here in this part I have 2 factor. So here also since GCD is 2, that means j will have 2 as a factor. So j must be even. Okay, so this information from order of power formula I get this information, and given this value I get this information. This j must be even. Okay, so what I will do, I will then go for brute force search. Okay, so exhaustively I will search only for j equal to even. So 2 square, then 2 to the power 4, 2 to the power 6, 2 to the power 8, like that, and modulo 59. And which one giving me 7, I check. Okay, so it is giving j equal to 80. So this problem is a very hard problem when your modulus is very large. Finding the discrete log of some element with base another element, it is a very hard problem. Okay, so you can feel how hard this problem is. Oh, this order of power formula gives you a very it narrows down your search space by half. Means you have to just search for j which are even powers. So only that information you get from this order of power formula. Okay, but you have to go for brute force. So finding the discrete log is a very hard problem, and based on that, we are going to discuss a public key encryption scheme. So in public key encryption schemes, mainly based on factorization hard to hard problems. Some problems are derive their security from the hardness of factorization problem. Factorization large integers is hard, like RSA. Another type of public key crypto systems are designed where they derive their security from the hardness of discrete log problem. This type of problem. Finding this j is very difficult from this congruence. Okay, so we are going to discuss that now. Elgamal crypto system, public key encryption scheme that derive its security from the hardness of discrete log problem. Okay, now okay, so here some problems are given, some exercises are given. You can try it out. How many primitive roots does n equal to 334 have? You can answer this very easily. Okay, what is the smallest primitive root? So if you are asked to find the smallest primitive root, you have to try from the lowest possible primitive root, from 2 Then if it is not primitive element, means successive powers you have to check. You don't have to check all the powers, only the factors of phi n you have to check those powers. And if 2 is not a primitive root, then you have to go for 3, then try for 5 like that. How many integers modulo 3, 3, 4 have order equal to 2? Okay, so these questions you can easily answer now. Same type of problem I have discussed how to solve. Just try. Okay. Okay. So Elgamal encryption scheme, public key encryption scheme over ZP star. As I said, it derives its security from the difficulty of solving discrete log problem for finite fields. So what is a discrete log problem in ZP? So given a prime P, so this ZP star means prime P, we have taken prime P. So so ZP star essentially ZP means ZP excluded 0, excluding 0. Okay? So discrete log problem in ZP is given a prime P, alpha and beta, where alpha is a generator of ZP star. Alpha is the primitive element of ZP star. And beta is another element of ZP star such that this congruence holds. Okay, so alpha to the power a is equal to beta modulo p. So p is given, beta is given, alpha is given. You have to find a, an integer a, such that a alpha to the power a is congruent to beta modulo p, where this a lies between 0 to p minus 2, including 0 and including p minus 2. So since alpha is a primitive element, alpha to the power and we are working on ZP star, alpha to the power p, alpha to the power phi p is 1. That means alpha to the power p minus 1 is 1. Okay, so we are not considering p minus. So this a alpha to the power p minus 1 is always 1 modulo p. I by Farmer's little theorem I can get that result. So this a must be an element of from this range 0 to p minus 2, such that alpha to the power a is congruent to 1 modulo p. Zero to p minus 2. Okay. So alpha to the power 0 and alpha to the power p minus 1 both are same. Alpha to the power p minus 1, since alpha is a generator, alpha to the power p minus 1 is 1. Alpha to the power 0 is also 1. Alpha to the power 0 means 1. Okay. So discrete log problem is this: given alpha, given beta, and given p, we have to find an integer a in this range such that alpha to the power a is beta modulo p. Now in Elgamal encryption scheme, we are given, we choose a very large prime such that discrete log problem is intractable in ZP. Okay, so if P is chosen very large, the discrete log problem is generally intractable. Means no efficient algorithm to find a discrete log. They solve this problem. So we choose P so that discrete log problem in ZP is very hard. Suppose ZP star is generated by alpha. So my plain text space is ZP star and ciphertext space is ZP star comma ZP star cross ZP star, Cartesian product. So one plain text element is encrypted to a ciphertext which contains two ZP star elements. Okay. Now key this for Elgamal we don't hide this P. This P is public. This P is public. This generator alpha is also public. This we also choose some a such that alpha and set alpha to the power a is equal to beta modulo p. Okay, we calculate this beta alpha to the power a. You reduce alpha to the power a modulo p, get whatever value, that is beta. So I publish p, this generator alpha, and this beta also. These are my public keys, and the secret key is this exponent, this discrete log of beta with base alpha. Okay, so this is your secret. A is the secret key and the public keys are these. So your key space consisting of all these tuples p, alpha, a, beta, such that alpha to the power a is congruent to beta modulo p. Okay, this alpha, beta are published, p is published, only secret is a. Okay, so as I said earlier, that while encrypting a message, encrypting a message from the space, the recipient's public key we have to use. So suppose A and B, A wants to send some message, some plain text, some message confidentially over a public channel to Bob. So A will use Bob's public key for the encryption. Okay, so this Bob means A means Alice, Bob, B means Bob, suppose. Okay, so B has a secret key, has his secret key A, and his public key is P, alpha, beta. These are all publicly available. The beta is alpha to the power A. Beta, alpha, P are known, but A is not known. A is kept secret to Bob. So when Alice encrypts a plain text. So what he does, he chooses a random element from ZP minus 1. ZP minus 1. Random k from ZP minus 1 and sends alpha to the power k and x times beta to the power k. Modulo working modulo p. So when while encrypting, Alice uses Bob's public key, P, alpha and beta. Okay, so what Bob computes, Bob chooses a random k from ZP minus 1. Okay, Alice has Bob's public key P, he can choose k from ZP minus 1, and Bob also has alpha and beta. So what he does, he chooses this key and raise alpha to the power k and also beta to the power k. He sends alpha to the power k and he masks the plain text, which is an element of ZP star, by multiplying it with beta to the power k. Beta is the public key part. Beta is the public key, alpha is also public key. So very simple. What the encryptor does, encryptor uses the decryptor's public key P, alpha and beta. A is not known to the encryptor. Okay, encryptor does not know A. So he has alpha and beta. He chooses a random k from ZP minus 1. P is available to him. K from ZP minus 1, raise alpha to the power k, also raise beta to the power k and multiply beta to the power k with x. So he sends alpha to the power k, this y1, and x times beta to the power k, this y2. Okay, so this is the ciphertext. So one plain text, which is an element of ZP star, corresponding to that ciphertext components is two ZP star element, y1 and y2, alpha to the power k and x times beta to the power k. So unlike RSA, in Elgamal encryption process, we introduce randomness. Some random element we choose and alpha to the power k, same, and x times beta to the power k is same, modulo p. So if you remember RSA crypto system, we simply take a plain text from Zn star and raise it to the power the public key b, x to the power b, that's exponent. There is no randomness introduced. Okay, plain text to the power b. But here we are utilizing, we are introducing randomness. Some random k we are choosing and is sending alpha to the power k and x times beta to the power k. So since we are introducing randomness, when ciphertext y1 y2 is sent over the public channel, an adversary has access, he can see this y1 y2, but by using brute force method he will not be able to, means its complexity of finding from the ciphertext, recovering the value of k or the plain text is very small. Okay, means compared to deterministic encryption scheme, randomized encryption scheme is more desirable. Okay, to prevent this brute force type attack. Okay, anyway, let us complete this. I will again come to that, how to, why this randomized encryption scheme is more desirable than the deterministic approach. Okay, so encryption is this. Now decryptor is having the secret key A. The secret key A, which is matching with alpha, beta, and P. Okay, this secret key binds the public keys alpha, beta components by this relation. Beta is alpha to the power A modulo P. So when decryptor receives this ciphertext y1, y2, this y1 and this y2, what he does, he has his own secret key A. Okay, so what he will do, he divide this y2 by y1 to the power A. So if you calculate y1 to the power A, what is the value? Y1 to the power A is essentially alpha to the power ka, and alpha to the power A is beta. So when you raise it to the power A, this becomes alpha to the power k. That means alpha to the power A to the power k. Alpha to the power A is beta, so beta to the power k. So here by exponentiating this y1 with A, y1 to the power A as a secret key, he can recover beta to the power k. This value becomes beta to the power, y1 to the power A becomes beta to the power k. So he can now simply this second ciphertext component, he can divide this second ciphertext component with this y1 to the power A, which is essentially beta to the power k. So beta to the power k is cancelling out, and you are getting back the plain text x. This is the idea. Okay. So while receiving y1 and y2, this is a ciphertext, you decrypt. How you decrypt? The decryption operation is done in this way. So y2, y1 to the power A inverse, whole inverse modulo p. So y2, y1 to the power A you can calculate using fast exponentiation algorithm. That the binary representation of A, and then keep on powering. All those things you can do. Finding the inverse, modular inverse, also we have discussed how to calculate this inverse. Okay, modular inverse, modular prime. Okay, so you can calculate all these values, and the correctness is written here. So y2 is x beta to the power k. y1 to the power A means alpha to the power k A inverse. So x beta to the power k, alpha to the power A is essentially, and this is alpha to the power k beta. You write the value of beta. Beta is alpha to the power A. Beta is alpha to the power A. So you write alpha to the power A k, this one, and alpha to the power A k inverse. So you are getting x modulo. So in RSA, I was discussing that part. This is the advantage of this scheme is the encryption scheme is randomized, unlike RSA. In RSA, it is deterministic. So when you in RSA, when you receive the ciphertext, any opponent can see the ciphertext. Okay, so x to the power A, that y value, y equal to x to the power b. Okay, y equal to x to the power b, you can see. Now B is publicly available. Okay, so he can try out all the possible plain text. Plain text space is also available. Okay, so he can check all the possible plain text and plain text to the power b. B is publicly available, so he can check for which value it is giving you the ciphertext. That way he can recover. So that exhaustive, you can go for exhaustive search on the on this public on this plain text space. Here, in Elgamal encryption scheme, that exhaustive search attack is more difficult to perform for an opponent. Why? Because here, not only the adversary, the opponent, not only have to try out for this, you have to try out for x for over this whole plain text space. The cryptography is very large. Not only on this, he has to try out this k also. He has to guess what value of k in zp minus 1 is giving you alpha to the power this value y1. So y1 y2 he has y1 y2 value. So he has to guess this k as well as he has to guess this x. Okay, that is difficult. So he has this alpha beta value, he has this this p, so he can always guess. But the problem is that complexity of attacking in this way, this exhaustive search, this is very large compared to RSA. So we always prefer encryption algorithm to be randomized to prevent brute force attack. Okay, so this is the difference between the probabilistic encryption scheme. This is probabilistic encryption in that way, okay, and the deterministic encryption scheme. Okay, I have two more problems in this. One more problem. Okay, so just quickly go through this. This is same type of problem. Okay, just within 5 minutes I can cover. So verify that g equal to 3 is a primitive root modulo 223. You can verify this. So 225, 223, you calculate what are the factors, and 3 to the power those factors. So 5 to 23 is 222, this value. So you have to check out all these powers, 3 square, power 2, power 3, power 37, then 2 at a time. 2 into 3, 3 into 37, 2 into 37, then whole power. Whole power you don't have to consider because it will always give you 1. So you have to check this, none of these is 1. Then only it will be a primitive root. So that checking you can do. Okay, so this is 1 and none of these 1. Then it is a primitive root. So first verify, you can do it. You know how to do it. Next is how many integers modulo 223 have order 6. So how many integers modulo 223 have order 6? If you get an element, if you take an element which is co-prime to 223, so how many elements have order 6? So that some element will have order 6 means 6 must divide 5 of 223. Okay, so this question is question number B. Let me see this one. Okay, so how many x are there in Z223? Means Z223 star, it should be star, such that its order is 6. Okay, so we are going to apply the power order of power formula. Since we have already observed 3 is a primitive root modulo 223, so x can be written as 3 to the power some j. J lies between 1 to 222. Okay, x can be written as 3 to the power j. J lying between 1 to 5 to 23. That means 222. Now apply the order of power formula. Order of so how many j's are there for which this order is 6? So by order of power formula, order of x means order of 3 to the power j is order of 3 divided by j, comma order of 3. So I have to find for how many values of j in between these, this relation holds. Means this relation holds means this value is 6. This value, this left hand side is 6. Okay. So this equal to, this is order of 3 is 222. 3 is the primitive element, and this value j 222. So I get this value is 6. So from here we get GCD of j 222 is 222 divided by 6. That means 37. Okay, so I can identify from this, I get this relation. So how many such elements are there which are having a order 6? So those elements are 3 to the power j satisfying this relation. Okay, so now this 222 is 2 into 3 into 37, and their GCD is 37. Means this j must be start from 30. They must be a multiple of 37. So 37 j in between 1 to 222. J is first one, j is 37. J cannot be 2 into 37. Okay, 2 into 37, then GCD is not 37. 3 into 37, it cannot be 3 into 37, otherwise GCD will be 3 into 37. 4 into 37, no. 5 into 37, next one is 5 into 37. So always you have to check whether this value is within this range or not. Then 6 into 37, no. 7 into 37, this value, this also possible, but this is greater than 222. It is out of this range. So only two values of j we can find for which this relation holds. That means there are only two elements which have order 6. 223 order is 6. So those elements are 3 to the power 37 modulo 223 and 3 to the power 5 into 37 modulo 223. Okay. Okay. And its order, there are two elements. So this question is answered. How many elements, and how many elements? Two elements. And if such element exists, find one. Third question you answer by yourselves. Okay, it is already done. You just go through it. And the last one is how many integers modulo 223 have order 74? Same type of question. Do it. Try to find. And how many integers modulo 223 have order 10? Okay, you do it. Same way you can find. Means first you have to check whether such order exists or not. So this order or this order exists or not. You have to check that. And if it exists, then go for finding this using the order of power formula. Okay, order of x modulo 223 equal to 74. How many you can find? How many I find? Total 36 elements here. For question number 6, question number C, I have found 36 such elements. And question number D, order 10. Order 10 means it does not exist. Okay, okay, so let us stop.